Good morning, everyone, in person and online to the second day of the Q2 user meeting. Again, today we have a very nice program prepared. So we will start with a keynote, which is also going to be streamed online. And for the participants here on site in Munich, we will also have 2 tutorials following this. Each of the tutorials will also be followed by a short scientific talk. And later in the afternoon, we will have the panel discussion, which will also be streamed online. But let's start with the invited talk of this morning. Today we're very happy to have Professor Stefan Filipp here with us. Stefan is a professor of physics at the Technical University of Munich and the director of the Walter Meißner Institute, also here in Munich. Before he had stations at ETH Zurich and at IBM Quantum, both in Yorktown and in Rüschlikon in Zurich, where he led a team that did development of architectures for quantum computing with superconducting circuits, which is also broadly the research topic that he still works on today. We are very happy that Stefan could join us today and that he agreed to give this talk and that he also helped us with the organization of this meeting. As many of you here on site will tomorrow be able to visit his labs at the Walter Meißner Institute. So, Stefan, looking forward to your talk. Thank you again.
Thanks, Clemens. Thanks for the very nice introduction. And thanks to all of you for being here, and thanks for the invitation. So it's really a pleasure for me to present our work on controlling of superconducting qubits, which I would also like to see on the screen now. And well, it did work before. Yeah, so now it works. Which is basically what we did since the last couple of years or so. And I have also to mention that the experiments that I'm showing here are partly performed at my time at IBM. And now we're continuing this at the moment also with experimental effort, but also in theory efforts in trying to control superconducting qubits, because I think that's the essence of it. We need to first improve coherence of qubits. We need to make it as good as possible, but then we also have to have good control capabilities. And that's kind of also where there is a good match between all the Zurich Instruments hardware and all the software and firmware, so that we get actually this handle on superconducting qubits to push this technology forward. So where are we? And that's just one introduction slide, not a lengthy introduction, because we all know where we are standing. We are standing here that we are seeing more and more roadmaps coming up on quantum computers, promising and also implementing tens, hundreds, or promising even now thousands of qubits in the next years to come. And I would say, well, this is kind of an exciting time still. One might see what is the promise and will it hold, but still looking backwards, I think it's a very exciting time in seeing what progress has been made in the last couple of years. And we have seen that most promising platforms like superconducting qubits and trapped ions are already on the market. And we're also seeing lots of development going on in the different countries. And I will also say a few words about our efforts here in Munich, what we are starting here, but there's efforts in Zurich, for example. There's efforts of the European level, in Swedish level, and there's also different other companies, but also different platforms. And one shouldn't forget about those. It's kind of just the field is going forward. And so in all of this, what is in common is that we need to be able to control our qubits properly. What is the next milestones? We have seen logical qubits. I guess that you have learned quite a bit in detail on the talk yesterday by Andreas. In what is really the goal is we need to build a universal quantum computer, and therefore we need logical qubits. But also people are looking for practical quantum algorithms, what we can really do with this quantum computer. And for this, we need to tackle these challenges that are ahead of us. So just briefly, what do we want here in Munich? There is a program the Munich Quantum Valley has started, and for this we want also to realize superconducting qubit quantum processors. And the interesting part is that we are doing this not as an academic institution, but we are doing this with research organizations and industry, and Zurich Instruments is also a part of it, or Roder and Schwarz is a part of it, where we try now to scale from the few qubits There's 2 qubits, 4 qubits, 9 qubits, and then for large-scale integration devices. So we are doing this from the hardware side, but we are also integrating a larger stack of different organizations or different groups here working on the full stack. So the goal is indeed to go from this hardware level, I'll say a few words in the next slide, up to the algorithms and the application level, where we have then the access to the computer over the cloud, and we have the theory, we have the programming languages, we have the architecture itself, but also the firmware, and then all down to the hardware. And for the hardware, we are focusing on superconducting qubits. But there is also other hardware platforms that we are pursuing, and that's trapped ion qubits. So where we trap charged ions in these linear arrays, and that's also one of the most promising platforms at the moment. And also neutral atom qubits. Here they're trapped here in arrays, but there is also different approaches now in that you can actually trap them with tweezers and shuffle them around, and there are several nice features that you can do with this, and that's also one of the promising platforms at the moment. For now, I want to focus now on superconducting qubits. What are the features? Just briefly, not going into detail. We have quantized nonlinear superconducting circuits, so we need something quantum in there, we need a qubit. The typical frequency ranges, and that's an advantage because we can use microwave frequencies, and they are readily available. And this gives us gate operations within a few nanoseconds. And that sets also this platform apart from the others in that we can do fast operations and can execute algorithms at very high repetition rates. We have high gate fidelities. 99.5% of 2-qubit gate fidelities are shown. One of the interesting points is that we have stable operations. So once it's kind of set up the system, we need to calibrate it, but it just runs. We don't need to care about switching it on and off again. We can have 24/7 operations, and that's definitely a good thing if you want to run a quantum computer that is remotely accessible. And also, we have fabrication that is scalable. So meaning, once we know that how to build one qubit, we can do many. That sounds not like the promise of Majorana qubits. But indeed, if we want, if we have the basic principles in how to do fab properly, we can actually make larger chips. We need to care a lot about the microwave hygiene and how to really do this properly, but still, we can scale this up and run the larger processors. What are the challenges? And I will come back to this, some of these. But thinking about is what is really why we cannot build a quantum computer right now. And one is quite generally scaling. We need to guarantee performance at scale. If we have single qubit gates or 2-qubit gates, which are 99 point something or so, then for a single qubit or 2-qubit, that makes sense, but we need to scale this up. We need to build larger systems. And that means we have to get cross-coupling, crosstalk under control. We need to be able to have uniformity, so basically the same parameters for all qubits, the design parameters. It's also the scalable control and the input-output. If you think about 1,000 qubits needing thousands of cables or millions of cables into the fridge, then we need to think about how to do this properly. Thermal budget size of qubits, all that comes in. Clearly, coherence. We need to have the quantum coherence over the as long as possible. So that means we have to work at the materials level. We have to identify loss channels, noise sources. There is this famous two-level fluctuators. Clemens can tell you in detail if you're interested in, which are kind of there, but nobody really knows what they are and how to get rid of them in all of the interfaces. There's also quasi-particles, ionizing radiation. That field has recently started in seeing that there is cosmic rays or high-energy radiation impinging on the chips and having some impact. Magnetic field fluctuations, and identifying these, and finally mitigating, either by design, by the choice of materials, or by fabrication. That's one of the challenges that we have to face and that we have to continue to get to the final goal of the quantum computer. And then there is control and readout. If you have solved these challenges, we also need to solve the control and readout, because we need to have pulses, and that will be the main part of the talk. We have to have pulses that are optimized so that we have these high-fidelity qubit gates that are not limited by coherence anymore, but also not limited by driving other transitions that we don't want. For this, we also need benchmarking sequences. We need to think about, is the pulses that we are having the best pulses? Can we design pulses that act not only on 2 qubits, but on multiple qubits? And can we have gates, operations on the qubits that brings us more efficiently to the state that we actually want to have for the quantum algorithm? And finally, there is the system level. So that means once we have the system, we need to automate the calibration, bring up the runtime environment, so just everything that you are used to have if you're just having a device that you can really use. So it has to run stably. You don't want to calibrate it. You don't want to care about it having a blue screen all of the time. And that's kind of, we need to think about also of the system level and having checks and how to run the system. Here belongs also characterization and verification. I'll talk more mostly about this control and readout, and also a bit about the scaling challenge. And there is 4 topics. Let's see how much I can cover. First, I want to talk about the optimal control for short pulses with high fidelity and low leakage. So having a single qubit, how can we optimize the control for getting the best performance? Then we are doing, at the moment, still theoretical work on optimal pulses for 2-qubit gates and multi-qubit couplers. And if I have time, I also want to speak a little bit about control of hidden qubits. You can think of it like, do I have to have control of all qubits? Or can I have actually some architecture where some of the qubits are hidden behind the wall, so to say, but still usable? So what is it about qubit control that is so special? Now, the basic principle is that we are sending microwave pulses in. These microwave pulses have an amplitude, they have a timing, and if you send this on the qubit, then you will drive a transition. So you'll bring it from the 0 to the 1 state, and doing this with different amplitudes, phase, and time, you can control the superposition state of a single qubit. In our qubits, you probably know, we have not only a 0 and 1 level, we have also the second level. So we have not a perfect qubit, but we have to deal with other levels that are around. And if you're driving now one of these levels with a microwave transition, it will happen that if you're not doing this carefully enough, that we are driving the transition from the 1 state to the 2 state, which is not a computational state. So if the qubit is in this state, it's kind of lost to us, and that leads to an error. So we need to shape and calibrate these pulses so that we stay within this computational subspace. The first thing that one can do, and that is a very prominent paper by Felix Motzoy in 2009, that was this drag correction. That means actually that instead of having just a Gaussian pulse is kind of the best compromise between spectrally broadening and then timing, so we use a Gaussian pulse, but that's not enough to avoid this leakage. So the idea is then we add another component. We add another component in the out-of-phase quadrature, in the Q term, so that's what you see here. And so we have basically an in-phase and out-of-phase quadrature with different functions. And if you do this properly, then we can avoid actually driving this 1 to 2 transition. Now, that's an analytic function that holds on paper, but it can be improved still. So getting to the more general form means now that we want to parameterize the pulses. So for each time step, we are choosing then a specific amplitude and phase of this pulse. And this can give us two pulses that are even better, that are matched to the specific qubit and to the specific qubit environment that it sees, that leads to level shifts and leading to that the analytical pulse doesn't work. So we are using these piecewise constant pulses, and the question then immediately is, so how can we actually know about the amplitude and phase here? We know the analytic function, but how can we actually know this, all of the amplitudes and phases at the different time steps? So we have many more parameters now, and that's then actually a question of how do we optimally choose these. And that now includes now, so you can think of, okay, analytically we can just, if we know about the qubit, we can just derive numerically what is the optimal pulse. But unfortunately that doesn't work because we have to take into account also the experimental setting, the chip, the environment of the qubit itself. So what we have to involve is now a closed loop protocol, which means that we are sending out the pulses. We send it to the experiment. We measure what comes back. So basically we measure what is the fidelity of the gate using a specific pulse, and then we adjust these pulse parameters and use a closed loop protocol to get to the best pulses that we can have for controlling the qubits. As a prior, we can use the pulse design, we can use these drag pulses that we send in first, and then we are following this closed loop protocol. And here it's essential actually to have good electronics, and good and even better electronics is needed for making this more and more efficient so that this loop is actually as short as possible, as fast as possible. Briefly, we need to measure the cost function. We need to actually identify the fidelity of the gate, and that we are doing by randomized benchmarking. So that means we are sending in a sequence of gates, that at the end we invert. So whatever we are doing here with a sequence of randomly chosen gates, we invert at the end so that ideally we are ending up in the ground state again. We repeat this sequence with random choices, and because we are kind of implementing always the identity, we can then figure out what is the gate error for each of these gates, what is the average gate error that is accumulated during this sequence of gates. So these gates are then pi-half pulses, or sequences of pi-half pulses, but we don't worry that much. So what we are seeing then is, depending on the fidelity of the gate that we are implementing, we are seeing an exponentially decaying curve. If everything is perfect, and the perfect means that we have, for short sequence, we have almost no errors. So then we are ending up in the zero population again. And then depending on what is the fidelity of the individual pulses, we'll see an exponentially decaying curve with the decaying constant depending on the fidelity of the gate. And here we see the number of Cliffords, and at the end, all ends up in a completely mixed state. So if you're focusing now on a specific number of Clifford gates, like this 200 here, and then just look how these curves evolve by changing the pulse parameters. And then we can identify what is the best pulses that we are having, because we want to maximize this cost function. And that's what's seen here. So we are starting with a cost function which starts off at the mediocre value at 0.5 here. And then by doing more and more iterations of this closed loop protocol, we are ending up with a high, with a cost function with a high value. Now the value doesn't tells us then how good the gate is. And from this, by running now this pulse with the final pulse parameterization, we can then figure out what is the actual gate fidelity of the single qubit pulses. And what we are seeing here, it becomes important actually for short gates. So here we have the pulse length, we have this pulse. For long pulses, it doesn't matter so much. The pulse parameterization, both for this drag, so for the analytic pulse, these blue points, and the piecewise constant, these red points, they coincide, and giving us a 99.9 gate fidelity. If we shorten the gates, then spectral leakage becomes more and more important, so we'll have this leakage out of the computational subspace. And if we just follow this analytic function, then we see that the gate fidelity drops for short pulses. With the piecewise constant experiment, we can actually continue and have a stationary or have a constant gate fidelity even for short pulses. And that means that our system, our closed loop control works, and that we can, even for short pulses, we can optimize the pulse so that we have a high gate fidelity. The limit at the end is the drive power. We could go to shorter gates, but at some point we need more input power. The pulse looks a little bit different than the analytic pulse. It doesn't. It has here this red pulse here. That's the pulse that we get out. And what's even more important, we see that this leakage, so that's leakage here, that's leakage into the second level, is actually suppressed. So if we plot now what is the amount of population in the second excited state for this drag, for these analytic pulses, and for the piecewise constant pulse, we see that this decay with the number of Cliffords is suppressed for the piecewise constant. So we are staying within our computational subspace by optimizing the pulse shapes. The challenge here is fast calibration of pulses. I've told you that we are doing this closed loop protocol, so that means we have to send in pulses, we have to redesign the pulse, the waveform, and upload it to the arbitrary waveform generator and do this closed loop. And that takes time, and also it takes time because we have to do this randomized benchmarking protocol. So the challenge is actually how can we improve the speed, how can we make this as fast as possible? What is the limit? One of the limits is actually, I told you coherence is good. T1 times relaxation time is good, so as long a relaxation time as possible is a good thing. The drawback is we have to wait, if we don't do anything actively, to actually reset the qubit to its ground state between each of the experiment that we are doing. So experiment 1, experiment 2, we have to wait until the qubit relaxes back to its ground state. And so if the T1 time is, say, 100 microseconds or even longer, you need to wait a significant, like 5 times longer than the T1 time. So this gives us a significant overhead. It takes a milliseconds to actually, so that we can start the next experiment. And that also means for the duty cycle, the 98% of time is spent on a qubit reset, waiting basically until we get the initialized qubit again. So we need to reset qubits. There's different options how we can do this. We can do this actively. We can actually measure the qubits, and then depending on whether we find it in the excited state, we do a pulse that brings it back to the ground state. We can also do this unconditional, so just sending in a pulse that whenever the qubit is in the excited state, it will be brought back in the ground state. The other thing that we were focusing or extending a scheme that was actually put forward by Leo Di Carlo's group, and we improved on that, is post-processing. We call this restless measurement. So what does this mean? In a restless measurement, we do the experiment, we measure the qubit, and we don't do anything but just start the next experiment, but we keep a record of what was the measurement outcome previously. So that means we know now in which state to start, whether it was a 0 and 1, and then can just run the next experiment, but with this knowledge, doing then in post-processing, identify what was the initial state of this experiment. So what does this mean then for the experimental sequence? What do we have to keep in mind there? So here I plot the IQ plane of the measurement point. So each point corresponds then to an amplitude phase of the microwave signal, which ends up at 2 different points in the IQ plane, depending on the state of the qubit. So for 0, it would be here, and for 1, it would be here. So if I just do this standard measurement sequence, then I would just start with a sequence of identities and doing pi pulses. So this x corresponds to a pi pulse. So I start off with an identity pulse. Then, if the qubit is in the ground state, I will identify it in the ground state. I do another identity pulse. It will be, again, I will be measured as a ground state. If I do then an x pulse, then I will find the qubit in the excited state. Then I wait, so it will relax back to the ground state. I do another x pulse, and it will again end up in this quadrature as a 1 state, and for the next time as well, because I always initialized. So what happens then if I don't do this initialization? So okay, and then the signal is kind of the difference between the 0 and the 1 here. I can take then as the signal of how much of the qubits are in the 1 state. So that's the standard way of doing measurements. In this different setup with the restless, then I would actually not wait in between, so I don't do the reset of the qubit. And that means the following, that when I do nothing, then I find the qubit in the ground state. If in the next experiment, I do nothing, then I find it in the ground state, and in the ground state again for a third. But now if I do a pi pulse, then the qubit will be brought to the excited state, but then I don't wait. So it will remain in the excited state, and then I do a pi pulse in the next experiment, and then I will find my measurement point. I would identify it as a 0 state. And the next X pulse would bring me back to the 1 state. So I see then the points jumping back and forth between the 0s and 1, and so we need to take this into account into the post-processing. That means now that the signal is not the difference between the 0 and the 1 state, but it's kind of the signal is the signal is just not the 1 state, but it's the difference between the ground state and the excited state. So we always have to see, is there a difference between the prior measurement and the one that we are doing right now? So we discriminate the data by qubit states 0 and 1 of the previous measurement. It turns out now actually that we just can't do this without putting more information in what is the errors that are connected if the initial state was a 0 and a 1. And so we have to take now into account that T1 decay and the pulse calibrations then also play a role. So we see this on these typical graphs of measurement fidelity. If the qubit is initialized in the 0 state, then if I do nothing, here the identity, I would mostly find my signal in this at the negative end, so that corresponds to a ground state. If I do an X pulse, I mostly find it in the positive on the positive side, corresponding to a excited state. And I see also some states, if I do nothing, ending up in the excited states. And this fraction here, compared to this larger fraction here, corresponds to errors in the measurements and the preparation. If it was in the 1 state before, and I do the same thing, if I do nothing, I find the qubit in the 1 state, but I have a significant fraction of these qubits that are then ending up in the ground state. And that's just because I need to wait a bit longer. So there's the T1 effect is actually more dominant if the qubit was in the 1 state. It has more chances actually to relax, whereas in the ground state it would just stay in the ground state. And this is seen that there is different error rates than connected to the qubit, the starting qubit in the 1 state or in the 0 state. But we can take this into account. We can do this in post-processing. So we take the signal that depends on the initial state in 0 and 1, and then split off the signal. And for each of these signals, we can do the analysis then and find basically what can be identified as a 0 and a 1 state. And that's shown here. So we have to take this orange and the green part. So basically, it's two different data bunches that we have to analyze differently. And if we do this, we can actually record the typical measurements that that one knows of, Rabi's, for example. We can do a standard Rabi measurement, and we can do a restless Rabi measurement, and the difference between them being very little. So there's almost complete overlap between the standard and the restless measurements. The difference being now that this Rabi is at the rate of 250 kilohertz, which is 250 times faster than what we are usually doing. So not milliseconds, but now in the few microsecond repetition rate. Also, the gain in execution speed for the randomized benchmarking is we're giving almost the same error per Clifford, 0.3 here, but with a much faster repetition rate. So we could speed up it by 50 times. Why the difference here? It's just because the randomized benchmarking sequence itself is just longer than just a simple Rabi experiment. So that's the limit, is then kind of the sequence itself that we are using, which sets then the maximal speed of the experiment. What's next? So the next thing is single qubits gates are nice, but the ultimate thing is is controlled phase gate, controlled gates creating entanglement in the qubit. So we need to find a gate that actually works well and creates entanglement between different qubits. We are currently looking in an architecture which has 2 qubits, or we are looking in architecture that has more qubits, but as a basic primitives, we're looking now into 2 transmon type qubits that are coupled via a tunable coupler. So while these can be fixed in frequency, the coupler can be actually adjusted in its frequency, and with this we are adjusting actually the coupling strength between these 2 qubits here. We can control the tunable coupler via magnetic flux, and we can change then in situ at the nanosecond time scale the coupling between the qubits. The challenge here is the same. We want to have short gates with a high fidelity, and we want to avoid leakage out of the computational subspace. And now this computational subspace gets actually a little bit more challenging because we also have the tunable coupler subspace that comes into play. So we also want to avoid that now some of the population leaks into the tunable coupler. So which gate do we want to have at the end? The gate that we are focusing on at the moment is the control phase gate, so given by this unitary. So what we want to achieve is that for both qubits in the 0 state, that's indicated by this one, or either of the qubits in the 1 state, indicating by these ones, we do nothing. But only if the qubits are both in the excited state, we impose a phase on them. And this phase is then actually the integral over the accumulated phase of over time. And this chi is actually the difference between having both qubits in frequency accumulated minus the frequency of the 1-1 state. So that's kind of the phase that is only there if the qubits are in the 1-1 state. Now I mentioned computational subspace or I didn't mention, so the computational subspace is now the qubits in the 0-1 or in the 1-0 state or in the 0-0 state, but we also have many more levels because we also have the coupler levels. And the tunable coupler that's indicated by this first column here, we see that there is many levels. And what we want to achieve now is that this state here, the 1-1 state of the qubit, this acquires a phase when we are changing the flux on the coupler, when we are tuning the coupler in frequency. And the coupler in frequency is, for example, this curve here, this pink curve, that changes in frequency. The qubits stay constant. And here is also the coupler in the 1 state and the qubits in the ground state. And we look now basically what happens to this 1-1 state, given that we are doing an excursion in frequency of the tunable coupler. The point is now we are going to a point in frequency of this tunable coupler where we get this chi shift. So this chi is basically the phase that is only acquired by the 1-1 state and not just the sum of the two of the qubit states. So we are looking now how can we actually form this trajectory in frequency space or in flux space so that we just acquire this phase with minimal time and with the best pulse available. And now how can we, just again, so that's kind of the time evolution of the tunable coupler, and we are looking now at the time evolution of this tunable coupler. And there's different options now that we can think of. We can just use Gaussian square pulses, so just the Gaussian having like the length, the amplitude, or the flanks as parameters. We can do now optimization of these pulses, and so that's we can find pulses with higher than 99.9% fidelity, but taking quite a bit of time, 51 nanosecond. And the question is, can we be faster? And if you look at the other side of the spectrum, if you're using the techniques or the trick that we used before, this piecewise constant decomposition of the pulse, we can get to much shorter pulse shapes. Then we could end up with pulses that are giving a 99.9% fidelity in 9 nanoseconds. The drawback is we're having then much more parameters to optimize over. It's 22 parameters, which is already quite challenging. And then, and that was actually work by Niklas Glaser, he looked into Fourier series. So basically decomposing the pulses into his frequency components. And a good trade-off seems to be with doing some 5 parameters, 5 frequencies, and finding them pulses that are about 15 nanoseconds in giving high fidelity. So if you focus a bit on that, and now I'm running out of time, so I skip over a bit about the technical details. We can find these pulse shapes that are parameterized in frequency space. We can look, for example, at these critical regions, because you might wonder what is this less steep curve here, and that's just because here we are entering a regime where there is an avoided crossing with another level, so we have to be a little bit slower than that to avoid non-adiabatic transitions. We can look at the evolution of the bare states, how much population there is left, and kind of also find now a way, because we are going back and forth across this avoided crossing, we can actually tune this timing properly and forming some symmetric pulses so that actually all of the states, all of the population that was then in this 0-1-1 state remains in the 0-1-1 state. If you're interested, talk to Niklas about this. It's actually very nice physics related to Stückelberg phase conditions, so doing interferometry. If you get the phases right, you can end up with pulses that if you go back and go back and forth again, and if you get the right phase at the center of this pulse, get the right phase accumulated, then we get two pulses where the population is still in this initial state and not leaked out of this computational state. The relevant circuit parameters, we did then some exhaustive studies of in parameter space. One of the critical parameters is qubit detuning on this axis here, and Kaplan harmonicity. So we were interested in what is the ideal Kaplan harmonicities and qubit detunings. And for these half Gaussian square pulses, one can identify then these islands or regions in parameter space where the infidelity is small, so where there's the lowest errors, and that's indicated by these purple regions here, which are quite small here, and that means that we have to really carefully select the pulses or the parameters to get to high fidelity pulses. But for this Fourier series, we then find that we can actually extend the range significantly of where we get pulses with low errors, these purple regions. So that means that here we have some stable regions where we where we estimate that the error in the gate is low, and so which would enable us to have high fidelity pulses for a wide range of circuit parameters. And that's done numerically, and the next step is clearly then to implement this in the experiment and also identify then the best pulse parameters for these fast gates. Briefly, I think I will skip the fourth point in my talk, but still want to address now what could go or what's beyond this. Because now 2-qubit gates is the essential gate that we want to have is a 2-qubit gate and single-qubit gates. But we could also think about, can we actually make gates that couple between more qubits? Can we get enhanced connectivity? Can we get efficient multi-qubit gates? So for example, if we are having now 2-qubit connectivity, so these green dots are qubits, and we have these red dots are lines between those. So if you're looking at the center qubit, to how many qubits can it talk to? It can talk to its nearest neighbors. It's these 4, and we need these 4 couplers in between. If you think of then extending this scheme and having couplers that could connect between, say, 4 of these qubits in the ideal case, then we could extend actually the connectivity to also these outer edges here. So we could, with actually less couplers, we could have a higher connectivity. So that's a nice incentive actually to look in what is possible in going from these 2-qubit couplers to coupler that can couple between more qubits. Now the ideal scenario is having 4 or even 5 qubit couplers. It turns out that we have to study first, can we implement 3-qubit couplers? Because as I said before, we have then states of the tunable coupler itself. We have a rich spectrum of different frequencies, which means we have to keep all of these under control, which is a challenge. So we are focusing now first on this 3-qubit couplers. Situation is the similar as before. We have a tunable coupler, which we can tune in frequency, and we have these 3 qubits. And we want to get now gates between, we want to get a controlled phase gate. So basically only when all of these qubits are in the excited state, they should accumulate a phase. The situation is similar to before. It's just that the energy spectrum, the level spectrum, gets richer. So instead of having now 2 qubits, we have 3 qubits, indicated by these 3 numbers here. And here is the tunable coupler. So here you see that the tunable coupler is tuned in frequency. It goes down as a function of coupler frequency, of flux, basically. And that's now the state where one of the qubits is in the excited state. These cross this, or there is an avoided crossing, so that means there's a level shift of this one state. We can also look into the state with 2 qubits excited, and we can, what is the interesting one, look into the 3 excitation manifold when when all 3 of these qubits are excited. And we want to look then at the shift that is actually given by this state here, this 111 state with 0 excitations in the coupler, hybridizing or interacting with other states in this 3 excitation manifold. And this would give us a shift that is only for this 111 state and not for the other states. We also see that there is these highs, there is more phases, so there's phases also accumulated for if only 2 of the qubits are in the excited state, which would give us a 3-qubit gate plus in addition 2-qubit gates. And that can be an advantage, but I will tell you in a minute that one can also find then a way to only single out these 3-qubit phases. So the Hamiltonian is then given by in this form. So we have these 2-qubit phases here, the first 3 terms, and we have this 3-qubit phase then in this gray part. And then we can look in this setup where we assume now reasonable couplings, so about, 70 megahertz or so between the coupler and the qubit. We can actually quite significant frequency shifts, and these frequency shifts tell us how fast the gate can be. So it's basically 1 over this, so we can get, in principle, gates which are fast, of the order of a few tens of nanoseconds. The point is actually that, as I said, we are accumulating not only this phase here, this 3-qubit phase, but we are accumulating also 2-qubit phases. So we want to have this matrix, where there's a -1 here, and all of the other entries here are 1s. And that means that all of these 2-qubit phases should accumulate to a multiple integers of 2 pi, and this one is a 2n plus 1 pi, so we get a pi phase shift on the 3-qubit. We can just wait long enough. We can have long pulses of the order of 10 microseconds, but that's a little bit longish, so we need to shorten this. And the scheme that we came up with is that we can do refocusing interactions. And not going into details here, that means now that we are doing pulses on this tunable coupler, not 1, but 4 of them in a row. We interleave this with pi pulses on the qubits so that we are permuting between the different basis states so that we can select them about plus and minus signs being acquired by the different states. And with this actually, with this scheme which takes of the order of 200 nanoseconds, we can get to 3-qubit gates using this tunable coupler with fidelity values of 99.6%, taking or basically assuming that we have no decoherence. And even with decoherence included, we get to gates that is in the order of 99% in theory. So again, the next step is kind of testing this in experiments, whether we can avoid all the population losses. That's also we investigated here, because if we don't do this phase conditioning perfectly, we will lose population. First, we'll scramble between the different basis states, or we will have leakage within the computational states, but also outside of the computational subspace. And here we can find basically also quantitatively what is the amount of leakage. I think I stop here I'll just tell you briefly, if I'm allowed to, maybe in 3 minutes or so, about the scalable control of qubits. Maybe just a teaser and then one of the results that one could actually have in mind. Because for scalability, what is the requirements? So I told you that control is one issue. We have to get these control pulses for all of the qubits, for all different gate combinations right. But there's also more materials engineering tasks like reduction of modes in large chips. If the chips get larger, then we have microwave modes. We need to address this. We need to reduce crosstalk. If we have arrays of qubits, we need to know how to arrange these qubits and how to avoid this qubit talking to the other qubits by some spurious modes or by some capacitive coupling that we don't want. And we also need to think about addressability. Thinking about we need qubit control, we need the couplers between the qubits. So that means we have to, depending on the architecture, and we need to read out, depending on the architecture, we have then 3 to 5 controls per qubit, which gives us millions of signal lines that enter this fridge, and that's clearly one has to think about what one can do. There's different ideas currently around, like one could just do brute force, high density wiring. That will bring us to a few hundreds probably, maybe even thousands, depending on thermal budgets, depending on packaging density. But that will bring us at least, I would say, to the 1,000 qubits, or to the hundreds of qubits and thousands of cables. One could go in this direction. Then there is actually ideas in using cryogenic electronics, electronics at the low temperature, so that we can then have digital control and create the signals and also the readout directly on the chip. Suffers issues from how good can the thermalization be, how hot will the electronics be at the low temperature stages, and so on and so forth. So that's a very interesting research field. I would say not mature enough to really assess what can be done in our millikelvin temperature range. Multiplexing is done for the readout. There is, in all of the Zurich Instruments, you can have multiplexing for the readout. We need to also think about multiplex on the control side, so that's certainly a way to go. There's also very interesting experiments where we can go into the optical domain, so basically creating fibers into the using fibers in the fridge, and then creating the signals using photodiodes at the lowest stage. Again, there is some proof of principle experiment that it works. Whether it's scalable, one has to figure out. And one thing that we thought about, you could also think about using less lines. So can one have some of the qubits behind that are not addressable directly? Because we always think about single qubit gates we need to have for each of the qubits, but can we save some of them and try to address them via the other qubits? And that's kind of what we did. So we thought about having, instead of having addressability on all of the qubits, leaving out a few. And what does this mean then for the couplers or for the gates that we need? And it turns out that this can be done. But the point is that we need extra gates. So we need, if we have only the readout capability of one qubit, we need I-swap and C-phase gates to actually be able to implement all of this. And that actually holds true also for the two-qubit operations. So if we have, instead of single-qubit gates and a single two-qubit gate, we can use now a single-qubit gate on one qubit plus an I-swap and a C-phase qubit, and still the system is fully controllable. And we have these gates available, which I don't go into detail now. We could then actually show in this setup that we can implement controlled phase gates, which having control only of about one qubit, but not of two qubits, but using C-phase and I-swap gates then in between to still extract the quantum process tomography, so still do this all the gates that are needed with decent fidelities. So that I skip now. and come to the summary. So that I've shown you that we did optimal controls for fast high-fidelity single-qubit gates, using also some speed-up schemes for getting high-efficient experiments with fast repetition rates. We are working now on optimized tunable coupler-based C-phase gate for fixed frequency qubits, simulating pulse shapes that would allow us for getting pulses in the 15 nanosecond range. Extending this to multi-qubit controlled phase gates. Also, the next step here would be to apply optimal control pulses using sufficiently capable electronics. And I also briefly touched upon this control of hidden qubit for solving scalability issues. And with this, I want to thank you for your attention, and I also want to thank my team members, my former ones and these here, for all the work that has been done. Thanks a lot.
Thank you very much, Stefan, for this very interesting talk. I'm sure there's going to be a lot of questions. Also, just a reminder for our online audience, if you have questions, just type them in and we will read them out for you. So, any questions? Yes, let's start here. Do we have a microphone to pass through? Yes.
Thank you. For the optimization of the pulse shape, what algorithm did you use? Gradient descent, evolutionary algorithms? What kind of stuff?
So that was a CMAS algorithm. So it basically means you're creating some cloud of different parameterized pulses. You send them in, and then you select basically which one is the best one. I think for a more detailed question, approach Max. He can tell you also the details for this. The problem is kind of that we cannot use some gradient descent because we don't know the gradients. So we kind of have to rely on basically the information that we get directly from the experiment. And that also, I didn't touch upon, this means actually that with the number of parameters, it was then, I think the largest one was this 55 parameters for the longest pulses. And then that's already a real challenge actually to optimize in a realistic amount of time. So that's clearly also a bottleneck, and there is research going on. What is the optimal, the best optimizer? I think if you have further detailed questions, just approach Max.
Thanks.
Thank you. There was another question just behind you. Yeah.
Hello. Yeah, thank you for the talk. So you mentioned that even with the restless measurements, RB is still at around 20 kilohertz, right? So does that mean that you are also looking at alternative measurements of fidelity, or is RB the answer? And that's where
no,
you're going to?
Also there, I don't think that RB is the answer. I think it's a pretty convenient method in just extracting the overall fidelity of the gate. Probably that's what we also investigating. Could one do with specific measurements that just tell you about one specific parameter? So like you're doing in the calibration measurements, you could use this as a cost function and then optimize for this, which would then also reduce the amount of time that is needed for evaluating this cost function. And that's definitely also a bottleneck. If you know kind of more precisely what is the errors, I think you wouldn't go for randomized benchmarking, but think about some other pi-half calibration sequence. But for getting a good estimate overall, what is the gate fidelity, randomized benchmarking seems to be one of the easiest tools to have.
Thank you. Let me also ask a question. In your two-qubit gate calibration, you had this map of two-qubit gate fidelities calculated as a function of one parameter was the anharmonicity of the coupler. And it looked like there was actually a very nice region for positive anharmonicity. So were you thinking of maybe using alternate designs for your coupler, like flux qubit-like, to explore this?
Yes. The point here is that there is also so many options for choosing couplers and qubits, and I think there is nice parameter regions, but then really knowing what is the best one, we don't have a good clue. So we are investigating actually whether you could use other types of coupling, like there's this snail type of couplers that you could use for this with more junction, which would suppress and also would in some parameters regimes also suppress then the crosstalk between the qubit or the CC type interactions. And I think I cannot answer the question now precisely what is the coupler to use, because we don't know the answer of this. But I also think that the coupler that we are using right now is kind of one option, but there's certainly other options available, and it's not clear to me what would be the best one.
Okay, thank you. Are there any more questions? Yep. Zadik.
Yeah. Hey, thank you for the presentation. Really big fan of your work. Now, when I look at your piecewise optimized pulses, they are piecewise in digital memory. Then they already, when they leave our instruments, they will be smoothened out, and then it continues. And so they sometimes look quite wild. When you either measure or simulate what actually arrives at the qubit, does it make sense? Like, can you see, this is what it's doing?
So for simulating, you have to take some filter function into account, basically that smoothens then the digital, the discrete steps out. So kind of that's taken into account. Whether the question is now whether it makes sense, yes, sure, it makes sense to do this.
Yeah, like when you then see what the end result actually is, can you see, it's actually a pre-emphasis and this is what it's doing, and actually it is a drag pulse after all once it's at the qubit? Or is this beyond kind of measurement and simulation capability?
The point is you would like to know what is the pulse arriving at the qubit. And that's then the difficult part. We could kind of measure what comes out of the instrument and also take this into account in the simulations, because we know then the response function at the output. But what we still don't know is how the pulse looks like to the qubit itself. And this is, I don't have a good answer whether that's doable. One could think about having some pickup or whatsoever, but at the end, the qubit is the best pickup, and there is you have to use the qubit states then to calibrate, and then we are back to the question, what is the best cost function measurement, or what is the best measurement of the response function at the qubit position? I think there might be still something to gain from getting a little bit better intuition in how the pulse looks like at the qubit, and we are doing this in simulation. At the end, I think we cannot avoid having some kind of closed loop protocol which does the last optimization on the fly.
Yeah. Yep. Thanks.
Yeah. Thank you. And there's another question, Andreas.
Yeah, nice talk, Stefan. I was wondering, what do you think the prospects are for these multi-qubit couplers? Do you really think you will successfully be using them in larger lattices, or to just improve connectivity overall, which would certainly be nice?
I was actually very optimistic, and now I'm kind of probably a little bit more realistic. We thought about having these 4-qubit couplers. Shouldn't be a problem at all. We see now that it's kind of, with all the different levels that we have to take into account, it will be a challenge to actually get to good qubit gate fidelities. We see now that there's some work going on also from Chalmers' group, Irfan Siddiqui's group, in this multi-qubit coupler directions, which show actually decent gate fidelities. So my gut feeling at the moment would be that for the 3-qubit coupler, I think we should be able to get it under control, either with the scheme that we are using or some other scheme. Whether it goes beyond that and having really 4 or 5-qubit couplers, I don't dare to say at the moment. It seems pretty challenging, and maybe then one has to go probably also to different type of couplers where we can avoid having too many levels that are crowding our spectrum. So, and I think the question is then, can we shift away some of the levels and really have some reduced subspace that we have to take into account? So I think 3 qubits seem to work. More than that, let's see.
Thank you. Is there any more questions?
I think over there.
Yeah. One online, I think. Yeah.
Sorry. There's an online question, and I hope I say that correctly. It's hard to read. PWL optimal pulse is qubit depending on its topological location in the qubit connection network?
Sorry, I can't decipher that.
Yeah. Okay.
Probably a piecewise constant pulse. Philip, can you help?
Yeah.
Okay, then I can quickly. I have a follow-up question on the Restless procedure. So you do a lot of post-processing of the data if you do the Restless. So it seems to me that as soon as you have not single-qubit operations, but you actually have two-qubit gates involved, that this post-processing might become relatively complex. Have you looked at how this scales with number of qubits, and is it feasible to do it also for a large-scale algorithm?
I think for a large scale, again, Max has looked into that a bit in detail. For large scale, I think it doesn't work because it scales not favorably. The point is kind of that one uses it then for single or two-qubit gate calibrations, or some algorithms where you really want to be fast. And okay, maybe I should have pointed this out more clearly. I think this Restless, as long as you kind of know what is the output state that you're expecting, like what you're doing in a calibration measurement, then it's ideally suited for that. So a single qubit, a two-qubit gate calibration would kind of work directly. And for larger scale algorithms is then another problem, because then you have to maybe change even the gate sequence, which is an interesting thing to do. But then also because of this post-processing that you have to throw away data or cannot use it efficiently, that might, I don't know what the exact boundary is, but that will be challenging as well. So I think it's 1-2-qubit gate calibrations is the most obvious application for that.
Okay, thank you. Have we deciphered the question?
Yeah, I can maybe guess it. It's really a bit hard to read. So I think is the optimal pulse shape of the PwC pulse dependent on the location of the qubit in the overall qubit network? So that's how my understanding of the question.
That will be an interesting question, but we don't have the overall network yet in experiment. So it depends definitely on that, because that's actually maybe phrasing the answer a little bit differently. That's kind of the point, is that the qubit at different locations will have different energy level shifts from neighboring qubits, and that's kind of what we have to take into account. So we have to do this calibration for each qubit individually to get to these best pulses. So yes.
Thank you.
Okay, I don't see any more urgent questions. Stefan is still going to be around for everybody on site for more discussion. So let's thank him again for a very nice talk. And before we go into the coffee break, I have two quick announcements for the people on site, but already thanking our online audience for participating. For the people on site, two things to announce. So there's still the sign-up sheet for the in-depth tutorials tomorrow. So if you haven't signed up yet for any specific slot, please have a look what slots are still available and do so. And we would like to take a group picture today, just before lunch. So I'll announce it again after the next tutorial, but just don't run away, ideally, so that we can have a quick picture of everyone together. And now we will have half an hour of coffee break, and after that we will restart with a tutorial by Mark. Thank you.